Great. Yeah, so first of all, I did want to thank the organizers of the conference. It's been a lot of fun, a lot of great talks, so I'm glad I could come. And I'm going to tell you about work done with my student, Sanket Kirame, that is not quite on the archive yet, although it should be soon. Okay. And I want to start with just a little bit of motivation for why we started thinking about this project. So, as we know, if I have a closed quantum system, a generic interacting closed quantum system, and I put it at finite energy density, local observables, thermalize kind of no matter what state I started, and they do so rather quickly. But once you understand this, and you sort of know what you're looking for, you can also discover many interesting examples of systems that don't thermalize in this typical way, including things like many-body localization or integrable systems and so on, which never thermalize. But also, there are classes of systems that do thermalize eventually, but maybe along the way they have some interesting intermediate regime dynamics. So for example, this is a picture from a paper written with Nick and Vedika and Anusha Chandran, looking at the fidelity of eigenstates of some Hamiltonian that's perturbed by a Floquet drive and showing that, under the right conditions, you can get a regime where the eigenstate fidelity is really very long-lived in the drive period, okay? So you have this interesting, and in our case, we were proposing you can kind of use this to see quantum scars as robust to this Floquet driving. But the point is that, you have this interesting intermediate time regime. Why is it there? Because the Hamiltonian is sort of evading thermalization on the timescales which you would expect. Good. Okay. So I don't think I need to say anything to this audience about why it's interesting in the open system context to think about things that, avoid thermalization, at least for a while. And so that was sort of my original motivation, what I wanted to think about in the context of Lindbladian dynamics. But to understand what it means to not thermalize typically on typical timescales, we wanted also to have some clearer understanding of what it does mean in the case, again, of Lindbladian dynamics, to thermalize typically. So that was where we were coming from on this project. And so, to make that a bit more concrete, how do we think about typical thermalization in closed quantum systems? Well, the tool that we use most often is the eigenstate thermalization hypothesis, and it tells you two things. It tells you that if you look at the spectrum of a typical interacting Hamiltonian, that spectrum basically looks like, in the bulk of the spectrum, not near the ground state obviously, but in the bulk it basically looks like a spectrum of some appropriate ensemble of random matrices. And that simultaneously the eigenvectors, also look pretty random, and obviously there's some constraints with that due to locality and the fact that they have some energy density, but they kind of look as random as possible from the point of view of local observables, subject to some constraints about global conservation laws. Okay, so we wanted to understand whether there's any analog of this, in any kind of physical signatures of dynamics in Lindbladian systems, okay? Why Lindbladian dynamics? Well, that's a case where, again, we can describe time evolution by taking a matrix and, looking at its eigenvectors and eigenvalues, okay? And the appropriate ensemble of random matrices to compare to is known. Okay, so before I get started, I want to make a quick sort of comment about local Lindbladian. So for the purpose of this talk, think of this local Lindbladian as coming from a particular weak coupling limit of some local quantum channel, okay? So in particular, here's here's your favorite quantum channel. So these are sums of local terms. We take this particular weak coupling limit, and what you get out is dynamics that looks like this. H is a Hermitian matrix of your choice, otherwise known as the Hamiltonian, and this is the Lindblad equation. This is like a little caveat, but usually when you open up a textbook and you read about Lindbladian dynamics, it's often introduced in the context of coupling to a thermal bath. Here's a very nice looking thermal bath in Hungary. Okay, and this works really well if you want to describe a few qubits coupled to a bath. If you do this for a many-body system and you kind of verbatim follow the standard derivation of the Lindblad equation, you actually get something that's not local, okay? So it's not, there are interesting, kind of remedies to this, but for the purposes of this talk, just think we're not necessarily thinking about a system coupled to a bath. We're really thinking about some just, local quantum channels in this weak coupling limit. Okay, good. So a little bit of notation. So, how do we go from this Lindblad dynamics to some kind of matrix that we can diagonalize? Well, all you have to do is take your operators, could be, a density matrix or a, an operator matrix, okay? And we can write them as vectors, and then things that left or right multiply this guy we'll write as super operators. And when you do that, your Lindblad dynamics is described by the action of this matrix on the vectorization of the density matrix. And one thing that is important when we're looking at the numerics here is that, obviously, A was a D by D matrix, where D is the dimension of the Hilbert space. And so now these are D squared by D squared vectors, and we have to diagonalize D squared by D squared matrices. This obviously puts some pretty stringent constraints on the system sizes that one can look at numerically. Okay, good. So that's our matrix. And there's a couple of things, for those of you who haven't stared at Lindbladians very much, that are worth emphasizing about what happens when you diagonalize these matrices. They're not Hermitian, so obviously their eigenvalues are complex. And also, and something that's actually quite important when we think about the dynamics of these systems, the left and right eigenvectors are different, okay? There's an orthogonality relationship which says if I take the inner product of the left eigenvector at, some eigenvalue labeled by j, and the right eigenvector at some eigenvalue labeled by k, this is 0 unless j is equal to k, okay? But that's not true if I take two right eigenvectors, even at different eigenvalues, okay? And this is sort of important when you're actually kind of expanding things in terms of this eigenvector basis. And the other thing I want to flag is that we're using a normalization condition, okay, that looks like this, and you will see these alphas appear in a few formulas, and they are the inner product between LK and RK, okay? All right. So you do that, you pick your favorite, local Lindbladian, and you diagonalize the matrix, and you get out a spectrum that looks roughly like this, okay? So always in these pictures, the real, this is the real axis, this is the imaginary axis. Typically, if you pick a Lindbladian out of a hat, you will find a unique steady state. This eigenvalue is always lambda equals 0, meaning it doesn't evolve in time. And the other eigenvalues all have a, negative real part, and they come in complex conjugate pairs. That's just because the channel preserves hermiticity. And we get this spectrum, and, you can see, so here's a plot of the density of states averaged in the imaginary direction and real direction, right? And what you can't really see in this scatter plot, but you can see in these densities of states, is that really there's not very many states down here, okay? And the spectrum has this nice well-defined bulk, which is kind of this lump out here. Okay, good. So we have our spectrum. What do we compare it to? Well, the relevant ensemble of random matrices are called Geometries matrices. They're just, independently distributed, random complex entries, okay? And how should we compare our spectrum to that of a Geometries matrix? Well, a very nice barometer that was introduced by Thomas Prozin and collaborators is called the complex level spacing ratio. And what this is, maybe I'll do a little, I forgot to put in a picture. Okay, but here in the complex plane is my eigenvalue lambda j, right? And I go and I find its nearest neighbor, which is somewhere here, right, in distance, and its next nearest neighbor, which is lambda j n, okay? And I just make a complex number, which is the ratio of these two differences, okay? So for the particular spectrum that I showed you over here, here's a plot of what that looks like. These ZJs obviously are distributed on the unit circle. And maybe to see a little bit more of the structure here, you can look at the distribution in both the radial and the angular direction, okay? And you can compare these to what they should look like for Geometries matrices. You can see here that the comparison for the full distribution is pretty good, okay? So this is what we mean when we say that our Lindbladian satisfies RMT statistics. Good. Okay, so in the following, I'm going to show you data from a couple of different sets of models, just to convince you that it's not that I've picked a particular Lindbladian. The first is what we call the dissipative Ising model. I take the Ising Hamiltonian 1D Ising at a non-integrable point, and I add some jump operators. The second one is we call the random model, okay? It's really important that these random models are translationally invariant. So what's random is I pick, you know, a set of two-body terms for my Hamiltonian randomly and a set of one- and two-body dissipative terms randomly, okay? But it's not, this is not, don't think disordered, okay? This is translation invariant. Okay. And one thing that I do want to highlight is that, you know, when you pick these at random, and here in this dissipative Ising model, you know, generically you expect that not all of the jump operators are Hermitian, okay? So we have some non-hermiticity built into the jump operators themselves. I'll come back to what this, you know, means for the model a little later. Okay, so, you know, here's our models. Here's some comparison to not the full distribution, but just the average of the radial and angular distributions here. You can see the angular one is a little bit more sensitive, so here's the angular one for a whole bunch of different random models. Okay, and the main takeaway here is that, you know, yes, all of the models we study, at least by the time we get to system sizes of 7, are like, you know, reasonably close to this Genebri state. And the ones that I'll show you from the random ones are more the ones down here. Okay. Good. Okay, so that's our models, and that's the sense in which they obey RMT statistics. So now let me start by, you know, coming back to what we would do for ETH, and one of the most important parts of ETH is what it tells us about the eigenvectors of the Hamiltonian, okay? So this is the sharp statement of ETH, and basically, you know, this here is a kind of randomly distributed Gaussian variable, okay? This, basically, the statement is that the fact that these guys are, you know, as random as possible in these matrix elements, given the constraints of energy density and locality, this is kind of important for how our systems thermalize. So we want to understand the nature of the eigenvectors also in these Lindbladian systems. And to do that, there's kind of a really important difference that I want to highlight here, which is that, you know, locality and dissipation really talk to each other. So I'm going to start by giving you some intuition for this in just a model where I only have dissipation and I have a bunch of single site terms, okay? And let's go ahead and look at these single site eigenvectors of this model. So the right eigenvectors, the right eigenvector with 0 eigenvalue, this is the steady state density matrix. It's kind of whatever you want, subject to the constraint of trace. Our normalization is a little different here. P is just the purity in the steady state, okay? So it has an identity piece, and of course it has some weight described by this vector beta on the 3 poly operators, okay? For the left steady state, so the left steady state is the steady state of operators. Obviously the identity operator does not evolve under our dynamics, so the left steady state is always 1. Now, because of this orthogonality relation, so all of the eigenstates, the right eigenstates with different eigenvalues have to be orthogonal to this left steady state. So that means that they only have weight in polys, okay? So they all have poly weight 1. Whereas the left, you know, kind of decaying states, I'm probably going to say excited states at some point, so that's what I mean, right? These guys, you know, have some component on the identity and some component in these polys. Great. Okay, so that's very simple single site model. Let's see what it tells us about the spectrum, again, of this, you know, toy non-interacting model. And to do that, just to get a feel for what this is doing, let's suppose that all 3 of these decaying modes have the same decay rate, which I'm going to call gamma. And let's ask what an eigenvector with eigenvalue minus m gamma, okay, looks like. So we can start with right eigenvectors. And to get eigenvalue minus m gamma, on m of the sites of the system, I have to choose a decaying mode, right? That has poly weight 1. On the remaining sites, I choose the steady state, and this could give a contribution of poly weight 1 or 0, okay? So then we see that the right eigenvector, you know, with this decay rate minus m gamma, has to have poly weight at least m. Again, in our non-interacting dissipative model. For the left eigenvectors, the left steady state is 1, right? And so I have n minus m sites where there's definitely not a poly, and on the remaining sites, there may or may not be a poly, okay? And so that says that the corresponding left eigenvector has poly weight at most m. Good, okay. So this is, again, this is a toy model. Obviously, we want to talk about generic Lindbladians, so you might be like, well, how much should I believe this? So, but I want you to use this as some intuition to kind of look at what we're seeing in numerics. And so what I'm going to show you is a plot of the kind of distribution of the eigenvectors. A here is going to be a right or left eigenvector over strings of different poly weight, right? So Fm is like, you know, if S naught is 1, Fm is all of the single site poly strings in my system. And so here's what that looks like for right eigenvectors, okay? Now remember, our non-interacting model basically said that, you know, if I'm going to have a high eigenvalue, I need to have a high poly weight, okay? Sorry, I actually cut off the legend in this, but, you know, this is poly weight 1, 2, 3, 4, okay, all the way up to 7, okay? And we can see that, you know, although we don't see this sharp fall off to 0 that our non-interacting model predicts, we do see in this dissipative Ising model, we do see this general trend that you have to have a high poly weight if you want to be talking to the bulk of the spectrum. And in fact, in this nice paper by the Ueda group, they actually showed that at least local operators are, you know, kind of, this is not just the numerics or finite size, that these guys are necessarily exponentially suppressed in the bulk of the spectrum, in the case specifically of local operators and their overlap with right eigenvectors. Okay, here's the same plot for left eigenvectors, right? Remember that our non-interacting model predicted that the high weight polys are going to be really strongly suppressed in these slow modes for the left eigenvectors. Okay, and here's what that looks like. Okay. Good. And just to show you that this isn't just this, so now we can look over different, you know, random Lindbladian models, okay? Again, random translation invariant, okay? And we find, you know, many of them look qualitatively similar to the dissipative Ising model, right? This one is really, the left eigenvectors are really quite evenly distributed in the bulk of the spectrum. The right eigenvectors, you know, again, have this, they do care in the bulk of the spectrum quite a lot about the size of the operator. So we have some cases that look, you know, qualitatively similar to what I just showed you for the dissipative Ising model. We also find some cases where the left and right eigenvectors have the same structure. This is because, so if the jump operators are all Hermitian, then the steady state of the Lindbladian is the identity, and then left and right eigenvectors have similar constraints. So this can happen if your jump operators are somehow not non-Hermitian enough. And the third thing that oh, sorry, question, yeah.
Can you say again, for left eigenvectors, I understand that you want to be high up in the spectrum, we have a lot of poly weight.
Yeah.
Can you say again what the conclusion for the right eigenvectors?
So good. So for the right eigenvectors, so for the left eigenvectors, if you know, in our toy model, decaying at a rate m times gamma, so m excitations, means that you have poly weight, right? You have, that means you have to put the identity on all the other sites, so you have poly weight at most m. For the right eigenvectors, it's the opposite. The excited guys have to have poly weight 1, and so then it's like poly weight at least m. Yeah, yeah. And so, and that's, so, and you see that reflected, you know, this is the length 1 operator, right? And so in the non-interacting model, this guy would just be 0 after this, right? Because it has poly weight 1, so it could only sit in this sector of the lowest, you know, the slowest mode, right? And similarly, this 2 guy, it would go out a little bit and it would fall to 0. And so this is, you know, correlated with this fact that the right eigenvectors, really these local guys, fall off really quickly throughout the spectrum. Whereas for the left eigenvectors, again, we see these instances where, you know, it's sort of, you know, poly weight at most m, and that means that in these low-lying guys, you're really strongly suppressed in the low-lying modes, in the longest-lived modes. Okay, and one interesting thing, and I'll come back to this later. I'm not going to show you the full distribution plots because I think they're maybe a bit. I have them if anyone wants to see them after. But let me just highlight. You know, sometimes, okay, if you work in a regime where the dissipation is overwhelmingly dominated by gamma 2, that is by 2-site terms, you also turn up models where, in fact, the longest-lived mode is actually very big. What do I mean by very big? It has high overlap with something that's order the system size, okay? And you can see that this is an interaction effect. This is a plot of the size of this longest lived mode for a particular choice of random model as we tune gamma 1, keeping gamma 2 fixed. And you can see that as the system gets bigger, you need stronger interactions to see this, but we do see it occasionally. Okay. So what is the moral of all this? This looks a little bit confusing, but the basic moral is that the eigenoperators of these local Lindbladians are not random because they have this structure that cares about the Pauli weight of the operators. Okay, and this is true, especially for the right eigenvectors, even though we have these somewhat different instances of that dependence. Okay, and there's another paper that explores this in the limit of strong dissipation for kind of k-local terms where it also holds. Okay, so then we can say, okay, well, we have this strong size dependence. We might hope, if we want to see kind of some generic dynamics, that the eigenvectors are basically pretty random given the constraints imposed by size dependence. You can measure that in various different ways. Here's one that we looked at that I like. This is the inverse participation ratio over the Pauli strings in each weight sector. Okay, these dashed lines are the value that you get for an ensemble of non-local random Lindbladians. Okay, which is basically just proportional to the number of Pauli strings in that sector. And you can see that these inverse participation ratios, come pretty close to saturating this in the bulk of the spectrum, whereas for these longer-lived states, we obviously have a lot more structure. Okay, good. So we have some notion of randomness, but we have to be careful to bear into consideration when we ask, where random matrix theory can matter. We have to bear into consideration this strong dependence on size. Okay, so that brings me to the next question, which is, okay, what quantities could be sensitive to this random matrix behavior of the bulk of the spectrum? And to understand that, it's useful to stare at the formulas. Sorry, I forgot the kind of ket around this guy. Okay, it's useful to stare at the formulas for time evolution of both density matrices and operators. And the first thing that I want to highlight here is that when I look at the time evolution of an operator, right? Suppose A naught is maybe a single site Pauli, that the part that picks out which eigenvectors, which eigenvalues it talks to a bunch is its overlap with a right eigenvector, right? And remember, these single site right eigenvectors fall off very quickly as the real part of the eigenvalue gets bigger. And so basically these local operators, time evolution of local operators, is essentially never really controlled by the bulk of the spectrum. In finite size, you can see some effects from the bulk of the spectrum, but in the thermodynamic limit, these guys really always live kind of on this edge where this is not what we're talking about. And so the observables that we looked at that care about random matrix theory are observables that are not linear in the density matrix. The second thing to note is at what time scales can this bulk of the spectrum matter, right? And here's a very basic point. The real parts of these eigenvalues are non-negative. This is an extensive spectrum, meaning that as you can see in this plot here, the mean of these eigenvalues, the mean of the real part, grows with n, okay? And so, and again, even though this is not always so apparent in our finite size numerics, we are talking about, when we talk about behavior that's controlled by the bulk of the spectrum, we're talking about very early time scales, times on the order of 1 over n. Okay. So that means that inasmuch as we can see RMT signatures at all, we're talking about some kind of universal early time decay. Okay. Why might this happen? Well, basically, the idea is that once we get to like high weight things, if these eigenoperators are reasonably randomly distributed over the bulk of the spectrum, then once we once we take our decay rate and average it over a small window, that's going to be very insensitive to the initial state. Okay. So here's a picture of these overlaps. This is an ensemble of pure states, and we're looking at their kind of overlap with right eigenvectors in some little left eigenvectors in this case, because it's a density matrix, in a small window of the real part of lambda. And this here kind of indicates what we would consider to be the bulk of the spectrum. And the error bars here are the standard deviation over this ensemble of random pure states Okay, this is an ensemble of mixed states composed of two pure states. And you can see that indeed, these fluctuations are small. And so we expect that for these guys, the early time dynamics kind of only depends on the appropriate analog of energy density for the specific quantity that we're looking at. Okay? So for the purity, that quantity is essentially the average real part of the eigenvalue. And here's a plot of what that looks like for some different ensembles. Okay? And the thing that I want to highlight here, okay, and here's these dotted lines are fits to, kind of a prediction of the early time behavior. And the shading here shows you the variation over an ensemble of, random states of a certain category. And the thing that I want to highlight is that in the early time behavior here, these shadings are quite thin. So once you get to sufficiently late times, there's really not that many eigenvectors that you can talk to, and so it's maybe not that surprising that the variance is small. After all, everyone does go to the same steady states, okay? But at this early time, of course, you're talking to a bajillion eigenvectors in the bulk of the spectrum, and we still see this universal kind of early time decay. This is not only visible in the purity. If we look at, nonlinear observables in the density matrix that involve operators as well, you can also see it. So this is a Rényi 2 correlator. What I like about this is that, purity is essentially only sensitive to the dissipation rate. This guy is sensitive to both the Hamiltonian and the dissipative dynamics, okay? Which is why it has this strong dependence on the dissipation rate. But again, you can see that we have this early time behavior. There's very little variation there, depending on what we, who in our ensemble we pick. And that up to some, short time, okay, so this is our early time, it agrees pretty well with the kind of fit based on the analog of the energy density for these states. Good, okay. So yes, this gives us sort of a barometer for what we mean when we say generic Lindbladian dynamics, and now you can go out and talk about the early time behavior of your favorite Lindbladian, and you can compare to this. And for example, if you see that, different initial states decay very differently in terms of their purity or Rényi 2 correlators, then you can say I have a model with atypical Lindbladian dynamics. Okay, and I want to end with, maybe a couple of comments about the dynamics of local operators. This is, again, not something about the bulk of the spectrum, but I think there's a few comments that I want to make to do with these size distributions of the eigenvectors. Okay. So here again is this formula that describes the time evolution of an operator. And so let's kind of go through the two, and here's the distribution of right and left eigenvectors. Let's go through the implications of this for local operators. So here's, again, the size distribution as a function of the real part of the eigenvalue of our right eigenvectors. Let's suppose that A is a single site operator, so it falls on this blue curve, okay? So then we see that this single site operator couples primarily to slowly decaying modes, right? Whereas if A naught were a high weight operator, maybe kind of extensive in the system size, then it would couple, most strongly to the bulk modes, and it would decay much faster. Okay. Not surprising, bigger operators, there's more places that dissipation can sort of poke holes in them, and so this is completely expected. What do the left eigenvectors tell us? The left eigenvectors tell us who this guy is going to evolve into over time, okay? And in particular, at long times, right, these bulk modes freeze out, they decay more quickly, and you're always dominated by these kind of longest lived guys at the boundary of the spectrum over here. And the fact that generically, right, or typically, these longest lived guys are, very heavily dominated by low weight polys is telling you that at long times, most local operators, well, in fact, most operators, even if they're not local, are going to be short, low weight polys. Okay, and that gives us a very kind of anticipated, intuitive picture of operator growth. Right, so here is a plot of kind of the size of our operator as a function of time, as measured by the average poly weight, right? And obviously, if I don't have dissipation, we see operator growth. It grows to something on the order of the system size and stays like that. And then as you go, as you turn up the dissipation, right, from the weak dissipation limit to something more generic, we see that at most the operator grows a little bit, and then it shrinks. Now, there's sort of two parts to this dynamics that I want to highlight for what I'm going to say next. So when we ask about the time evolution of an operator, there's sort of two things going on. The first is that under Lindbladian dynamics, the norm of an operator is not conserved. This is like, trace of operator squared, okay? And these norms are shrinking, and they typically shrink, with the decoherence rate. And for single site depolarizing noise, you can actually show this analytically. And more generally, certainly the single site dissipation is definitely shrinking the operator norm on average. Okay, so one way that an operator approaches the steady state is simply that its weight, the kind of norm of the operator is getting smaller, and what's happening is these excited modes, okay, these faster decay, these longer weight polys are just sort of going away, and that's one of the ways they go away. The other thing is actually, to do with the structure of these lower lying eigenmodes, that you're going from left eigenvectors that are maybe to some degree in the bulk of the spectrum, okay, to left eigenvectors that are long-lived, and those are typically small. So you can also track the size distribution of operators. And again, by the time we get to sort of maybe more generic dissipation rate, we can see that a single site operator, has time to grow a little bit into a two-site operator and a tiny bit into a three-site operator before dissipation kind of kicks in and these coefficients are just gone. Okay. So this is kind of the generic case. This is, really not, oh, and I should say, Ehud's group had a paper, kind of modeling these kinds of effects in random circuit models. So it's kind of the generic case. But what about these cases, right? So we said that the left eigenvectors are telling me what kind of operators are present at long times. What about these cases where the size distribution is atypical? In these cases, we can see some sort of funny signatures or unexpected signatures in operator growth, okay? And I want to be clear, what I'm plotting here is, so in order to see this growth, I have to pick an operator whose expectation value in the steady state is 0, okay? So I'm taking my favorite operator and I'm subtracting off its steady state value, okay? And then, here's a plot for different system sizes of the average length of this operator as a function of time, okay? And again, this is the distribution of lengths, right? So the norm is still going to 0, but we can see that, in as much as the operator is not 0, it's dominated in this strongly interacting limit. It's dominated by operators that are kind of order the system size, whereas in the typical case, once I subtract off the steady state value, it's dominated by operators that are kind of basically polyweight 1, okay? And this is what the corresponding size distribution looks like. So so in other words, this idea that, kind of the slowest decaying non-identity operator is always small is not always true when we look at this limit of strongly interacting dissipators. Okay. So, I think the main moral is that, yes, random matrix theory does have something to tell you about the dynamics of Lindbladians, but you have to look at early time, and observable is nonlinear in the density matrix. The eigenvectors do have this structure that's strongly constrained by locality, but otherwise pretty well scrambled, so that's sort of why you can see this at all. But we see some interesting variations in this locality structure, which you can observe in the dynamics of local operators at late times. Okay, thanks.
Thanks, Fiona. Thanks, Fiona, for the nice talk. Any questions?
Yes, thanks for the nice talk. I just want to quickly clarify, so the Lindbladians considered here, like the dissipation, are all translation invariant? There's no spatial disorder?
Yes.
Do you expect that to have any impact on these results here?
Yeah, okay, so we didn't look at spatial disorder, but actually the paper, okay, somewhere in the slides, so there is a paper by the Ueda group where they were looking for analogs of many body localization in Lindbladian systems. I do think that strong disorder, because we're very finite size limited, and this is very hard to study, but the fear is that certainly at finite size, if you put in a bunch of disorder, your spectrum is not going to look generic, and therefore, that could be a different class of things. Yeah, and they claim some non-genericness of dynamics and so on. but yeah, I think it's an interesting question, and you know, maybe there's a lot that can be said. Maybe there's, you know, maybe the numerics are so limiting that it's hard to say much. Yes.
In these examples where you have this like very large weight, slow mode, do you understand what goes on physically? Like what mechanism gives rise to those?
No, we don't have a kind of analytical model of what's going on. I think there's kind of, if you thought about, you know, kind of, you can sort of think about a circuit model, right? And one thing that's true is, you know, when you have single site dissipation, right, you know, it can sort of turn things into the identity. These two site dissipators, I mean, they can also create entanglement, right? That's sort of, or they can also, you know, grow the operator. But the quantitative, you know, kind of the kind of exact mechanism, we see this in some but not all models when you turn the single site dissipation off. It's not atypical, okay? So it's not it doesn't appear to be something super fine-tuned, but we don't understand the exact mechanism of what's going on.
So I may have missed it in the beginning, but did you study the similarities between local random Hamiltonians and local random Lindbladians? Of course, there are lots of differences, but are there parallels?
Okay, good. So I think so the first thing I want to say is when you have ETH for a Hamiltonian, this is a very powerful thing because it tells you about like long time quantities, right? It tells you that, you know, in the long time limit, local observables thermalize. And so in that sense, this is very different, right? And basically it's very different because the bulk of the spectrum is totally, you know, all of those guys decay exponentially in time, so it's totally gone by the time you get to anything close to the long time limit. However, I think the analogy is basically that, you know, in the bulk of the spectrum, you do have eigenvectors that, you know, subject to constraints that are very important that come from locality. They do otherwise look well scrambled, and that tells you that, you know, if you look at, you know, if you pick a state out of a hat, right? You pick a pure state out of a hat and you look at, for example, how its purity evolves over time, this is something that doesn't care about the details of the initial state. And so in that sense, it's similar to, you know, sort of similar to ETH. I initialize my closed quantum system in some state, right? And I'm not very sensitive to the, you know, like after a reasonably short time, I'm not sensitive to the details of that initial state, except, you know, I only care about things like its energy density. So that's the analogy that we're trying to make. Does that help? Okay.
So if you had to formulate like a similar statement of ETH in forms of like, you know, matrix elements of local observables, how would you go about it for, like, what would be your equivalent of the Srednicki ansatz for Lindbladians?
Yeah, good. So, oh, maybe I should put somewhere we have a formula. It's a while back. It's somewhere. Is it here? Nope. Okay. It's here somewhere. Let's see if I can find it. But yeah, so I think that here it is. Okay. Yeah, so the first thing is that, so, you know, now, so you can look at, I mean, you actually can look at like matrix elements of super operators, right? So again, these are the kinds of things that enter into, you know, into like things like the Regnier 2 correlator. And so those do have a similar form. So, you know, you have these random coefficients. They are, you know, basically like Gaussian distributed. And you have some exponential suppression as you look at eigenvalues that are very different. And so, but, you know, the kind of, the long time behavior simply isn't there, right? So you can compute some average of the quantity in your initial state, but, you know, this is more telling you maybe about some early time behavior, if that makes sense.
So you would write something similar to this, but you're saying that the interpretation, like how it relates to dynamics, would be different.
Yeah.
Okay.
Yeah.
If you look at this eigen spectrum of a superoperator, they have a random matrix looking like bulk. We have some branches, which is much more simpler. So at early times, the random matrix universal behavior dominates, while after long times, they all wash off and you have like a branch, right?
Yeah.
Is
So,
there
yeah.
a reason why they should be separated? So are there some examples where these bulk extends to a very long time values, or?
Okay, so, I mean,
or is there a fundamental reason why? I assume that
well,
everything is 1D, so maybe it's 1D, you should go.
okay, so certainly we only looked at models in one dimension, but I think the basic thing is this. So the first comment is that, we are very finite size limited in numerics. We can get up to, n equals 8 roughly. And at n equals 8, right, if you look at like the operator dynamics and you look at the time scale where these bulk modes freeze out, like it's not super early, okay? But the reason that I don't want to make claims about, say the impact of the bulk for local operators and so on, is that in principle, if I could get to n is 50 or, 20 even, right? In principle, this bulk of the spectrum, it is extensive in n, right? Here's the mean as a function of n. Here's the standard deviation as a function of n, right? So it is genuinely true that, you have these low-lying modes are always, in principle, separated from the bulk, okay? And so I think, like I said, if you actually take our, I think I don't have the plot in here, but, if you take our operator dynamics and you can plot, where in this operator dynamics does the bulk freeze out, okay? It's not at some time scale that's, separate from this evolution, of, operator growth changing and so on. But I believe that is probably a finite size effect. And so that's why I don't want to talk about this in that case. Is that what you're asking?
I know, but I was wondering, is there a family of Lindbladians where they do
where you could...
But these are very generic Lindbladians, but are there other families?
I see.
Integrable Lindbladians?
Well, I mean, so one thing that's also true, right, is there's some, I mean, the answer is, your question is, can I cook up some model where that's true even at pretty strong dissipation? I don't know. I haven't thought about that. So I don't have an example. That's the only thing I can answer. The other comment, right, is that there is some the other, instance in which the bulk is small, right, is if I take the weak dissipation limit. So if I take my dissipation and tune it down with 1 over n, then this bulk is going to be close by, right? And that's when we actually have this picture of like, the cartoon picture is like, you mostly get unitary operator growth, and then only at, at very late times does it get cut off. Yeah.
Yeah, a very nice talk, and I enjoyed it a lot. So I'm just wondering about conservation laws. If you put in the conserved U1 or conserved G2, I mean, and these are really, zero form conservation laws. Does random matrix theory or random Lindbladians give you any insight?
Good. So, yeah, so the thing that I can say about that is, so when we have weak symmetries, I'm actually not so sure, right? But if we have a strong symmetry, right, which is to say that really, my Lindbladian leaves the charge, if you think about system and bath, right, so now the Lindbladian conserves the charge of the system by itself, then you really do get, as in the Hamiltonian case, you can diagonalize the Lindbladian by symmetry sectors. And so there the expectation would be that, if you get to big enough sizes, that you would see this generic dynamics within each symmetry sector. We haven't looked at the effect of weak symmetries, so I think that's an interesting open question.
Thanks.
Yeah.
I had a question about this slide. So when you say that extensive eigenvalues decay in like this 1 over n time scale, the decay doesn't just depend on the eigenvalue. It also depends on these like wave function overlaps, these alphas.
Yes, absolutely.
So is it obvious that it's really 1 over n, and you cannot get some like much longer time scale from like some blow up or like of those factors?
Right. No. So. Okay. So I guess I would say. Let me see if I have my. let's go back to the eigenvector plots. Yeah, so here's a sort of eigenvector distribution, right? And so, if I'm talking about operators, right, it's my overlap with the right eigenvector. The right eigenvector is overlap with the initial operator, right, that tells me kind of like what kind of eigenvalues I'm talking to. And then it's the nature of the left eigenvectors. So, I think all of these modes, let's suppose that I have an operator that, primarily lives in this part of the spectrum. So I think the thing is that, like, you, of course, do have, like, some dephasing behavior, which can, make things fall off more quickly. But all of these modes here do have an overall exponential decay with gamma. Now, the reason, okay, so that's kind of the first point, is that all of these eigenvectors. Now, if you look at the Rényi 2 correlator, actually, it's kind of interesting. Yeah, so here's my Rényi 2 correlator, right? And here we're actually dividing, by the purity, okay? And so that, this is actually why this guy is much more sensitive to J, to the Hamiltonian part. Because here, if you look at, you can do some early time Taylor expansion, okay? And this kind of leading order gamma term actually cancels between numerator and denominator. So I think, this is a case where you're certainly more sensitive to dephasing. But, again, it's important. If I don't divide by the purity, it's kind of like everybody is decaying exponentially, and this is kind of a dominant thing. Yeah, so it's maybe like, I think the answer to your question is yes, that's possible, but you have to choose your observable rather carefully.
All right, let's thank Fiona again.